All right, cool. All right, so this on the 10.5 homework, use any method to determine if the series converges or diverges. That's the reason for your answer for this awful looking thing here. So, I mean, just based on the multiple choice answers, there's only so many things that we could try. Geometric series and the ratio test. This is definitely not geometric series because we have this n factorial here, and factorial stuff's not ever going to be geometric stuff. So we're going to have to use the ratio test. And then remember with the ratio test, this is where you want to look at that limit as our index values go to infinity. And it's that absolute value of the ratio. So a sub plus 1, all divided by that a sub 1. All right, so for us, in this example, that's going to be the absolute value of. So here, just replace it, right? Replace all of the n's with the n plus 1.
All right.
You do have to be a little bit careful about this numerator here because you're going to have to put that in parentheses like that. And then just divide it by the same thing with just regular n's instead. Okay. All right, cool. So does that look all right so far? Does that make sense?
Yeah.
All right, and then here's just kind of the trick to it. And I did this a little bit in the video, but what you want to do is we're not really sure about what's happening with the absolute values necessarily. The n plus 1 factorial and the n factorial, that stuff's all positive. It's only this part, but because of the negative sign and the absolute value, it's basically just going to make this negative sign disappear. So you can ignore those. This n plus 1 factorial, we're going to rewrite that as n plus 1 and then times n factorial, just using the definition for it. As far as the e goes, you're going to have to distribute. So in the exponent itself, it'll become a negative 16n minus 16. The denominator I'm just going to leave as is. Then, I forgot to get rid of that negative sign. For the numerator itself, now we're going to use the power rule, or the product rule, sorry, for exponents. This you could separate out. So let me just copy this over. We're going to separate this so that we have that e to the negative 16n and then just e to the negative 16 beside it. And then a bunch of stuff cancels out. The n factorials cancel out top and bottom, and then this e to the negative 16n cancels out top and bottom. So all we're left with is we're left with the n plus 1 from the numerator and then that e to the negative 16. And then from there, remember we're taking n as n goes to infinity. So because this n is just a linear term there by itself, if you take that to go infinity, it's just going to make the whole thing blow up. So this whole thing, it looks like it's going to go to infinity. I can't find my infinity sign. Infinity. Cool. And then don't forget that's that p-value. So from the ratio test, this is p. I think this is the second part of the test, but if p is bigger than 1 or if it goes to infinity, that just says that the thing has to diverge. So the series diverges because the limit using the ratio test is infinity. Does that make sense? Is there any questions about that?
That makes a lot more sense now.
Okay, cool. All right. Is there any other homework questions you guys want to look at? I was looking through the homework, but I don't think this first one's too bad. I think it's a lot of kind of repeating ideas.
Right.
Was everybody able to watch those videos that I put in Moodle? Okay, did they show up? Were they loud enough? Any criticisms?
I was able to see them, but they were a little bit quiet. I had to like put a headset over here.
Okay. I'll make sure I bump up the mic volume there. No other homework questions from any of the sections? I think the sections 3 through 5 are due next Monday. Okay, so for this question, use the integral test to determine if the series shown below converges or diverges. Be sure to check that the conditions are satisfied. They have this awful looking thing. Okay. So, of course, when you guys do your test, I don't know if I'm going to give you the ones that have these multiple choices on there because I think it gives it away a little bit. So let's first talk about the conditions part of things. If you want to test the conditions of the integral test, I think there's only two things that you really need to worry about. The first thing is that you have to make sure all of your terms are positive numbers, and that's what we have, right? If I plug in into this for any n, it's always going to be positive. The other thing that you have to have is that your sequence values are eventually decreasing. And I know that's kind of hard just to look at it and see if that's the case, so I would probably just use your calculator in this case, but I'll type it into the Desmos here. So 5x squared, that divided by e to the x divided by 4. So great. Yeah, there we go. Okay, cool. So if you notice that at the beginning, your function is increasing, and it's okay for it to increase at one point. It's just as long as it starts to decrease eventually. So when we're here at this value, and if you look, this value is at 8. Once I hit an index value of 8, my function starts to decrease, and then it decreases forever from there. So as long as it's decreasing eventually, we're fine. That's why these integrals are starting at 8 instead of starting at the value 1. So now we just have to do that integral. So just kind of copying it over here. Integral from 8 to infinity, that's 5x squared divided by e to the x divided by 4 dx. And what I would do first is I would rewrite this a little bit. So just bringing that e up to the numerator. So still going from 8 to infinity, but I'll write this as 5x squared e to the negative x divided by 4 dx. And unfortunately, there's not much that you can do here as far as the integral goes, except for using that integration by parts, which is going to be a little obnoxious. So here's my best attempt at writing that out. So remember, you have to select the u, and then you have to select the dv. You could pull the 5 out to the front if you remember to do it initially and then plug it back in at the end. I'm just going to leave the 5 in here for the u, and then the e to the negative x over 4 is going to end up being the dv. And then you're technically supposed to put a dx on the end of that. Okay. From there, you want to find the du and then the v itself. And this seems to be the biggest mistake that I see students make is getting the derivative and the antiderivative confused. So if my u is 5x squared, I'm going to take the derivative of that, du, which is 10x dx. But for the v, I'm going to take the antiderivative of dv. This is really e to the negative 1/4 x, and when you do the antiderivative, you want to bring the reciprocal of the coefficient down. So really we're going to be bringing a negative 4 down, and then leaving that e to be e to the negative x over 4. All right. So now rewriting this into the integration by parts. Remember, it's UV minus VDU. So we're going to do the 5x squared times this negative 4e to the negative x over 4. So it's negative 20 x squared e to the negative x over 4 minus, and then it's going to be the integral, still from 8 to infinity, of v du. So this negative 4 e to the next over 4 times this 10x thing. So we're going to have a negative 40, we're going to have an x, but we're still going to have that e to the negative x over 4 dx. And unfortunately, you just have to do it again. So another integration by parts. So set your u. The double negatives here cancel out, so I'll let my u be the 40x. dv will still be the same thing. It'll still be that e to the negative x over 4 dx. Finding the du, we get the du is just 40 dx, and then your v, same thing, negative 4 e to the negative x over 4. Plugging this in, this is still going to stay here. So this negative 20 x squared e to the negative x over 4. Remember that the minus sign canceled out with this minus sign, so it's going to be positive. And then the next set of u substitution, or the integration by parts. So uv, which is negative 40 times 4 is 160 x e to the negative x over 4. And then minus the integral, still from 8 to infinity, of v du. So that's negative 4 times the 40, so another negative 160 e to the negative x over 4. Last step is just doing that other integral there. So I'm just going to copy paste here. So that last integral, again, the double negatives cancel out, and again, you're going to be bringing down another negative 4. 160 times 4 is a number 640, so negative 640 e to that negative x over 4. We don't have to worry about the plus e here, because we are going to be putting in those limits from 8 to infinity. Okay, so just to kind of plug those in, when you plug the infinity in, I don't want to go like too in detail with it because it's just too much to explain here. But the polynomials aren't going to do much compared to the exponential. The exponential is really going to drive this, and because it has a negative exponent, it's going to go to infinity in the denominator, which makes every single one of these terms go to 0 when you plug in infinity. So we're just going to ignore that. Minus, then we're going to plug in 8 into all of this stuff. So we get that negative 20 times the 8 squared times e. If I plug negative 8 into this fraction here, it's going to come out to be negative 2. And then minus 160 times the 8 times e to the negative 2, and then minus the 640 e to the negative 2. Okay, I'm not even going to bother simplifying this down because it doesn't matter. It's a number. Because this simplifies down to a number, that means that my integral simplifies down to a number, which means that it converges. So that's good enough for me, but of course it's not good enough for the homework. You would have to actually simplify this down to figure out what it is. But they all have e to the negative 2s, so you would just combine all the leg terms together. I have a calculator in front of me. Let me do it real quick. I think I got 3,200 e to the negative 2. Let's try it. Oh, yay, we did it. Okay, great. So yeah, so that's how you do this integral test here. And I think unfortunately the hardest part is just that integration by parts, which you have to do twice, and then keeping all the negative signs in order. The more important part for this question is knowing that you need to do integral test to solve it. And we need to do the integral test because it is something that we can take the integral of, but more importantly, it satisfied those two different conditions, that it had to be positive numbers and that it had to be decreasing forever. Now, if the question was just asking you, does this thing converge? I think the ratio test might even be easier to do than this integral test here. Okay, cool. Was there any other homework questions you all want to look at? If not, we don't have to stay the whole time. I just wanted to put this together in case there were questions you wanted to see worked out. With the comparison test, remember what you want to do is you want to use that theorem. And what the theorem said for the comparison test is to kind of look at how the things behave. There's two different versions. There's just the normal comparison test, and then there's the limit comparison test. This one's just asking you to do the normal comparison test. So we want to compare 5n plus 6 divided by that n times n plus 1 times n plus 2. And basically want to know, is this less than or equal to 5 over n squared for forever and ever and ever? I don't know if there's an easy way to do this. I think you're just going to have to plug in numbers for n to figure out which one of these is bigger than the other one. I'm almost certain that we're going to figure out that it's going to be less than or equal to. I say that because it's the only way that this is going to come out to work out. But just plug in big values for n and see what happens. So just to try one, like if I were to plug in n to be maybe 50, I'll just plug it in my calculator here. So I got the first thing to be 0.00193. And if I plug it into the 5 over n squared, I get 0.0002, or 0.002, sorry. So yeah, it does work out, right? This thing is bigger than this thing as my n gets larger. So because I know that, that tells me that the series has to converge. This series converges because this, remember, is a p-series, and as long as that exponent is bigger than 1, it converges. So because this thing converges, and this thing is always bigger than this thing, then this has to converge as well. So by the comparison test with this, the series converges. Josh, which question was it that you hit the Ask My Instructor for? Is it one that we looked at already? Okay. All right, cool. All right, so we got some time. Anybody else? Any other homework questions? Ten point seven, number 2. Was there a sheet for the comparison test you were going to hand out? Yes. There was, and there still is. I'll just have to email that to everybody. I'll do it as soon as we hang up here. I'll have to find it in my stuff. But I'll email that out. All right, so for 10.7, number 2, consider the series. We have this awful-looking thing. Find the series radius and interval of convergence. For what values of x does the series converge absolutely? For what values of x does the series converge conditionally? So we can look at this stuff. I haven't made any videos yet for this one, but if you're working ahead, which is totally fine, we can talk about it real quick. This stuff isn't due until not next week, but the week after, I think. So with radius of convergence stuff, this is when you're going to start having variables in your series values themselves. You're going to be using the ratio test to figure it out. So basically what we're going to do is we're just going to force this to be the ratio test and figure out when does it converge. So to do the ratio test for this, remember that that's going to be that limit of that absolute value. So we're going to look at the absolute value of -1, and then we're going to plug in n plus 1 in for all of the n's. Correct. It's not going to like me. All right, we're starting over. So -1 to the n plus 1, and then there's going to be 2x plus 8 to the n plus 1. And then that whole thing divided by, so -1 to the n times that 2x plus 8 for this time just to the n. Close the absolute value. So what the absolute value is going to do here is it's just going to basically make these -1s disappear because they're not going to do anything. Then you're going to end up with 2x plus 8 to the n plus 1 divided by 2x plus 8 to the n. This is going to simplify down just to be the absolute value of 2x plus 8. Right, you're going to have n plus 1 on top and n on the bottom, so you're going to have 1 left over, and then the absolute value is going to come on the inside to be this absolute value 2x plus 8. Don't forget that from the ratio test, this is what we consider the p-value. We don't have to take the limit as n goes to infinity because all of the n's just disappeared. This thing's limit as n goes to infinity is still just that thing. Remember that for the ratio test, this p-value, we need to be less than 1. So basically what we're going to do is we're just going to force that 2x plus 8 absolute value to be less than 1. This is something that you should have seen back in algebra class. Anytime you have the absolute value is less than a number, you're going to squeeze it. So we're going to do -1 is less than 2x plus 8 is less than +1. Subtracting 8 from both sides. And then dividing by 2 on both sides. We get this. So -9/2 is less than x is less than -7/2. So when it asks for the radius and the interval of convergence, this is the interval of convergence. Our series here converges as long as my x is in between these two numbers. You just have to be a little bit more careful about it, is because we don't know if these are going to be just less than or if they're going to be less than or equals to. So we need to test them. So let's first test x is equal to -9/2 and just kind of see what happens. So if x is equal to -9/2, then my series is going to be -1 to the n still, and then 2 times -9/2 plus 8 to the n. But that we can simplify down a little bit. So it's still going to be the infinite series. Still have that -1 to the n. If I multiply this stuff all out, I get 2 times -9/2 is just -9, plus the 8 is going to be -1 to the n. -1 to the n times -1 to the n is just 1, right? If they're positive, they multiply together to be 1. If they're both negative, they multiply together to be 1. So you're taking the infinite sum of 1 which is 1 plus 1 plus 1 plus 1 plus 1 plus 1, that goes to infinity. Okay. So in other words, negative 9 halves is not going to work. That's definitely not going to converge. We also have to test the other endpoint, which is that x is equal to negative 7 halves. So we're going to do the same thing. We're going to plug that into here. All right, so plugging negative 7 halves into the x. So now 2 times negative 7 halves is negative 7 plus the 8 is going to give us a positive 1. So we still have the negative 1 to the n out in front. And then this came out to just be positive 1n. So positive 1 to the n is just nothing, just 1. So that means that we're going to simplify down to just be negative 1 to the n. But negative 1 to the n as an infinite series just alternates. Plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. It doesn't go to infinity anymore, but it still diverges, which means that x is equal to negative 7 halves doesn't work either. Right. So that gives us our interval. Our interval is going to be that negative 9 halves is just less than x is just less than negative 7 halves. So just to type it in here. Okay. The radius of convergence, you want to think of the radius of convergence as the halfway distance of the whole interval. Think of this as being a circle on the one-dimensional line. So the radius is just going to be the halfway distance across. So if I'm going from negative 9 halves to negative 7 halves, that's a total distance of 1, which means that my radius is going to be a half. Okay, so what values of x as a series converge? Absolutely. This goes back to the ratio test. Remember, for the ratio test, if you prove that something converges with a ratio test, you have proven that it converges absolutely. So this entire interval, this negative 9 halves x less than x less than negative 7 halves, that whole thing is where it converges absolutely. It also asks for this last part, where does it converge conditionally? This does not converge conditionally anywhere. If you did find that it converged at one of the endpoints, then that would be where it converges conditionally. But it did not converge at any of the endpoints here, so it just converges conditionally on the endpoints. All right, so kind of a hard one, I know. And then I hope when I get around to making videos of this radius of convergence stuff, maybe this will be a little bit easier once you see some more examples.